Mechanical waves, part 2, transverse and longitudinal waves. So another way that we can classify waves, and probably a more important way to do it, is to classify them by the motion of the particles. Again, this slide kind of gives you a definition and a description. The next slides are going to show you graphically what it looks like, so you can really get a good sense of it. By definition, transverse waves are waves in which those particles move perpendicular to the direction of the wave. The slide that we saw previous was a picture of what a transverse wave looks like, and you'll see another one in a moment. There's plenty of examples of transverse waves, some that you might be familiar with. For example, if you drop a pebble or something in a small puddle and you see those ripples go out, that's a transverse wave. The wave that's on a musical instrument, a stringed instrument like a guitar or violin, the kind of wave that's on that string that creates that sound is also a transverse wave. There's earthquake waves. Earthquakes actually generate two kinds of waves. One type is transverse. It turns out that light's a transverse wave, and that's something that we'll study later on in the course. And then, believe it or not, in its own way, those waves that people do at a stadium are also transverse in nature. On the other hand, longitudinal waves are the case where the particles move parallel to the direction of the wave. And again, we'll see what that looks like in just a moment. And the most important example of that are sound waves. Sound waves are longitudinal waves that travel through air. And it turns out that earthquakes also produce, any earthquake event produces not only transverse waves, which are S waves, but also P waves, which are transverse, that are, I apologize, longitudinal in nature. So here's kind of a mechanical transverse wave kind of isolated on its own slide. So the item that's causing the disturbance is going up and down, and because all of these little particles are attached, that up and down motion over time gets propagated across the string, but none of the particles again move all the way down to this end and come back. The particle that's right here just continues to move up and down based on the passage of the disturbance. You can compare and contrast that with this longitudinal wave. So here again is the same kind of spring. You might visualize it as a slinky. I think that's a good way to go that everybody's familiar with. And if the person whose hands here is moving back and forth left, right, what it does is alternately compresses and allows the springs to expand. And that alternation of compression and expansion continues to move down this elastic medium, this coil, which is free to move. None of these individual coils, though, travel any great distance. They move back and forth locally, the way I'm indicating here. But that alternating a region when the coils are moving back and forth and they're at a point where they're close together, you visualize that compression. At points where they're spread out, because more of the coils are here, there has to be less here, that's expansion. And this actually is an example of the same type of motion involving sound waves. This is actually a photograph of sound waves where these areas here in the black are where the air molecules are very close together. These areas here in the white are where the air molecules are less densely packed. And what's interesting is, while this doesn't look like a sine or a transverse wave, if you were to plot the density of the air along this disturbance as it moves, high density here, low density here, and you plotted it along the way, you get a graph that, interestingly enough, has that wave, that sine wave shape. And you might think your only options are transverse and longitudinal waves, which we've been taking a look at. But it turns out you can have a combination of the two, and that's what water waves do, surface water waves. If you're not very close to the shore, but approaching the shore, what happens is, and maybe you've experienced this if you've been out in the water as the swells are coming in, a wave comes in. Initially, it lifts you up. It pushes you back towards the beach a little bit. It drops you back down. and then it draws you back out, and you get that sense of that circular motion. And what's happening is the particles aren't just going left, right, as they would here. They aren't just going up and down as they would in the transverse wave. What they're doing is both at the same time, and so you're tracing out that shape of a circle. But it's still that repetitive periodic wave behavior.